Okay, welcome back. So we've looked at our classification of differential equations, and we've explored one possible solution method for linear first-order differential equations, and that was the integrating factor method. So let's have a look at an example where the integrating factor method might be applicable. So here we have a body of mass m, which is dropped from rest at time t is equal to 0. We're also asked to not neglect drag, but assume that the drag is proportional to the velocity v. And we're asked to find the velocity as a function of time. As we know, the motion of a rigid body is governed by Newton's second law. Newton's second law, again, states that the sum of the forces, and again, we're just going to look at it in a single dimension, so we'll call this y, is equal to the mass times the acceleration in the y direction. Now, because we're asked to find the velocity as a function of time, we can recast this as a differential equation by saying that the acceleration is equal to the velocity as a function of time. Okay, so next step is that, as always, we look at a free body diagram. So we're just going to assume this bean-shaped object is our free-falling body. That could be a skydiver or really anything that is falling from a high altitude. Okay, and before we continue, let's set up our coordinate system. What we're going to say is that downwards is positive. Let's draw the forces acting on the body. So again, these, with a free body diagram, you draw the external forces acting on the body. So we're going to have the force of gravity, which is the weight, and we also have the drag force, which is opposing the motion. So the drag force, which we'll call F drag, we are told to assume that the drag is proportional to the velocity. So we're going to say that it is equal to some constant k multiplied by v. This leads to our equation of motion, which states that, again, keeping in mind our coordinate system, so we're going to have the weight, which is acting in the positive direction, so we have mg, and then we have the drag, which is acting in the negative direction, minus kv, and that will be equal to the mass times the acceleration. Let's put this in a bit more familiar form. So we have the mass times the acceleration plus the drag force is equal to mg. So what I'm doing here is trying to cast it in standard form, where in standard form you have your dependent variables on one side, and then anything that is left over that is not multiplying a dependent variable, in our case v, will go on the right-hand side. So now this is not quite in standard form, because as you recall, standard form requires that whatever is multiplying the highest order derivative, here the first order derivative, must be 1. So what we're going to do is divide this whole equation by m. Doing so leads to dv by dt plus k over m multiplied by v will be equal to g. So this is the ODE that we're looking to solve. As you can see, this is a linear first order ODE. Linear, because we don't have any nonlinear terms such as v squared or dv by dt to the power of 3 or anything like that. And it is first order because our highest order derivative is a first order derivative. Therefore, we can use the integrating factor method. So recall that the integrating factor, so before we had it as mu x when we looked at the derivation of the integrating factor, because in our general form we had x as the independent variable. But in our case, the independent variable is t, so we're going to call this mu t. So recall mu t will take the form of e to the power of the integral of p of t dt. So that's our integrating factor. So now we need to find what p of t is. So you go back to your standard form and you will see that p of t is this term over here. So mu of t becomes e to the power of k over m dt. Now k and m are independent of time, so these can be taken out of the integral. So all we are left with is e to the power of k over m multiplied by t. So now recall that our solution will take the form v of t will be equal to 1 over mu of t multiplied by the integral of mu of t multiplied by r of t dt plus a constant of integration. So we've already solved for mu of t. So now we need to find what r of t is. Well, that's fairly simple. That's just this term here. So let's substitute this into our general form for the velocity. So we have 1 over e to the power of k over m multiplied by t multiplied by the integral of e to the power of k over m multiplied by t, and all of this is multiplied by g dt plus c. So carrying out the integration, we find that we have 1 over e k over m t. So g can be taken out of the integral. So we just have the integral of e to the power of k over m t dt. So that leads to m over k, and then multiplied by g, e to the power of k over m multiplied by t plus c. So carrying on over here, we can simplify the solution of our differential equation by noting that these two terms are the same, so we could cancel this out over here, and then we will just have the constant multiplying the e to the power of k over mt. So let's write this out. We have v of t will be equal to mg over k plus c multiplied by e to the power of minus km, k over m multiplied by t. Okay, so we still need to solve for our unknown constant of integration c. And with that, we use our initial condition. We're told that at time t is equal to 0, the velocity is equal to 0. This is our initial condition. So let's substitute this into our solution. So we have a velocity of 0 is equal to mg over k plus c. And now we know that e to the power of 0 will be equal to 1. Therefore, c is equal to negative mg over k. This gives us a final solution. V of t will be equal to mg over k minus mg over k multiplied by e to the power of negative k over m multiplied by t, which can be simplified to mg over k multiplied by 1 minus e to the power of minus k over m multiplied by t. And that is the solution to our differential equation. Now I invite you to pause and think about what this solution might be suggesting. What might a plot of the velocity as a function of time look like? So just to be clear, this constant k is a physical constant, or a constant that is somewhat dependent on geometry. And we'll see what this looks like later on in the course. And you will definitely see this in your study of fluid dynamics. So let's have a look at our solution. I'm just going to write it out over here again. So think about what the velocity is for small times t. So if we set t is equal to 0, then this term over here will be equal to 1. So then this whole bracketed term over here will be 1 minus 1. So the velocity at time is equal to 0 is equal to 0, which makes sense. As we can see, with increasing time, this term here, this exponential term, will become smaller and smaller, right? Because this is essentially 1 over e to the power of k over m multiplied by t. So as t gets larger, the denominator gets larger, and therefore the fraction becomes smaller and smaller, and less important. And for very large t, this will become so small that it becomes unimportant at all, and essentially becomes 0. And therefore you will just have 1 minus 0. So for very large times, so let's say t goes to infinity, the velocity is just equal to mg over k. And this is what we call a terminal velocity. So let's plot this. Let's see what this might look like. So if we have on the x-axis time, and on the y-axis the velocity as a function of time, so we know that at time t is equal to 0, it will be equal to 0. And as t goes to infinity, we approach some value. And that value here is mg over k. And so what this looks like is something like this. Where the velocity approaches a constant velocity, or the terminal velocity, as the time approaches infinity. Or let's just say as time gets larger and larger. And again, this is termed the terminal velocity. Note that this velocity is achieved by the object when its weight is perfectly balanced with the air resistance. That is, we could throw an object from a height or simply let it fall with no velocity at all, and it will achieve the same velocity as time increases. And that velocity again is the terminal velocity. This is a very interesting result. So our result for the maximum possible velocity that an object can achieve is independent of its initial condition. Let's recap what we did. We looked at Newton's second law applied to a free-falling body. We assumed that the drag force is directly proportional to the velocity v. This led us to a linear first-order differential equation, which allows us to apply the integrating factor method. This integrating factor method led us to a solution v of t, which is equal to the terminal velocity multiplied by 1 minus e to the power of negative k over m multiplied by t.